Hello everyone, this is Unit 10, Generalized Linear Regression Model, Frequency Approach and Bayesian Approach. We finished the multilinear regression, simple linear regression first, multilinear regression. In simple linear regression or multilinear regression, in these models, y follows normal distribution because y is continuous. Take any value within an interval, so we can assume normality. But in generalized linear model, in general, the response variable y doesn't follow normal distribution. It follows something else. So let's start by the logistic regression. So unit 10, generalized linear model or generalized linear regression model, frequency approach and Bayesian approach. And I will start by the simple case again, one explanatory variable and one response. And then we will generalize to any number of explanatory variables. So generalized linear model, frequency approach, generalized linear model, Bayesian approach. And I will let you know what is next. So let's start by a motivating example, studying and passing a course. What do we do when the dependent variable in regression is dummy variable? It is binary variable. Y takes only two possible values, 0, 1. Like fail, success, or the patient get improved and the patient didn't improve. Maybe 0 is someone has doesn't have diabetes, 1 has diabetes, and or 0 is not a poor person, 1 is a poor person, and so on. So why take only two categories, 0 or 1? One of them will be taken value 0 and the other one is 1. But you can keep them as has diabetes, doesn't have diabetes, and so on. But working with 0, 1 is much better. So how does the number of hours spent studying affect the probability of a student passes an exam? The number of hours is explanatory variable, and this one take any value. This is continuous random variable, is fine. But the problem is the response variable. In this case, the response variable is binary variable, passed is a course or failed is a course. Let's say passed is 1 and failed is 0. The explanatory variable in this case is the number of hours a student studied for an exam. So one thing we could do is simply run an ordinary least square regression. Why we do not use linear model? For many reasons. Why we do not follow the same approach we have covered for the simple linear regression? For many reasons. So let's cover this idea. This table shows the number of hours the student studied and the pass or not pass in the course. The first guy studied 0.5 hours, didn't pass. Second one, 0.75, didn't pass. Third one is 1, didn't pass. This guy studied 2.25 hours, passes the course. This guy studied 4.25, passes the course, and so on. So I uploaded the data set on Canvas and gave a name GLM data. It has two variables, the hours and the passing the course. And I grabbed this scatter plot. This is a scatter plot. Some people look at this one and say, oh, this is a linear relationship between X and Y. But keep in your mind, Y should be continuous. But this Y in this case take only two values, 0 or 1. But let's see what will happen if we use the simple linear regression to find the equations that describes the relationship between the passing the course and number of hours. If I use LM function and I gave the response and I gave the explanatory variable, the name of the data, it gave me this output. Because if you asked R to run the analysis with linear model, the R will not say no, do not use LM because the data doesn't fit the approach you use. R will give me some output. And R will not refuse analyzing these data. it gave me some output, but this output is not, I shouldn't get this one. I shouldn't run this one. When you look at the beta 0, you'll find it is 0.53. When you look at the beta 1, it is 0.003, and it is significant. And when you look at the p-value for the whole model is significant, the p-value is very small. But this one is not correct approach. If you follow this one, and you would like to write down the equations that you would like to use to predict it will give me the expected value, or y, the net value of y, which is y on average equal beta 0 plus beta 1 x xi yi. The expected value of y is pi, the probability of success. When you calculate the expected value of y, it will be pi, which is the probability of success, equal beta 0 plus beta 1 xi. So pi I, the estimated probability of success, equal beta 0 is 0.53991 plus 0.00311 xi. So maybe you would like to use this equation to predict the probability of success at some given value of number of hours. But the statistical analysis is not correct. The approach you selected to analyze the data is not correct. So why? Let's look at these guys. Let's look at the assumptions, because testing beta 0 is 0 or not, testing beta 1 is 0 or not, needs some assumptions like normality, constant variance, independent. Let's look at normality is satisfied or not. Normality for residuals. When I look at the histogram, looks like there are two groups. When I look at the QQ blood, I see normality is not satisfied, and I see two groups. When I look at the number of hours versus residuals, I see two groups. It looks like there is something wrong. And the normality assumption, the very important one, is not satisfied. So I shouldn't use this approach because the assumptions are not satisfied. I will not be able to test beta 0 is 0 or not, beta 1 is 0 or not. When you look at this one, if you conclude, you shouldn't, when you look at the previous analysis, this one, you shouldn't look at this one and say it is satisfied, it is significant, because the assumption is not satisfied. So you shouldn't look at this one, you shouldn't look at this one actually. So if you'd like to test this one is significant or not, this one is significant or not, you need to double check the assumptions. But the assumptions are not satisfied. This is one of the problems. Another problem is what? Maybe you are going to use this equation to predict the probability of success. And the probability of success is some value between 0 and 1. No way to have a probability greater than 1 or less than 0. And when you look at these fitted values or the predicted values, you'll find many of them are greater than 1. How it comes? This is a problem. Sometimes they give you negative values for the predicted, for the probability of success, which is doesn't make sense. So you see the predicted value is not correct also. So there are many problems. The assumptions are not satisfied. The predicted value may be greater than 0 or less than, can be greater than 1 or less than 0, can be negative. So you shouldn't use the linear model, the simple linear regression, to fit data or to find the equation for some data that the response variable is binary data, or dummy variable. You should use something called generalized linear model or logistic regression. But before I cover logistic regression, I want to make sure that you are familiar with something called odd ratio. So what is the odd ratio? The odd ratio is the probability of any event occurring divided by the probability of not occurring. So assuming the probability of success is pi and the probability of not successing, or the probability of failure, is 1 minus pi, This ratio is called odds ratio. So what is the meaning of this odds ratio? Is the number of times the probability of success. How many times the probability of success of the probability of failure? What do you mean? Let's have an example. For our example, the probability of success is 0.5. How did you calculate 0.5? I counted how many passes a course. I found it is 10 out of 20. So pi hat is 0.5. So the odds ratio is 0.5 times 1 minus 0.5 is 1. What does it mean is 1? It means the probability of success equals the probability of fail for this course. But what about if the odds ratio is 1.23? It means the probability of success is 1.23 times the probability of fail. So the probability of success is 1.23 times the probability of failing the course. If it is 1.23. If the odds ratio is 3, it means the probability of success for this course is 3 times the probability of failing the course. This is the meaning of the odds ratio. So why you are covering the odds ratio, I will let you know. Because the range of pi is between 0 and 1. So if I use this equation, if I use this one, expected value of yi equal beta 0 plus beta 1 xi, if I use the simple linear regression, it means I am using pi I equal beta 0 plus beta 1 xi equation. This is linear equation. And pi should be between 0 and 1. But if I fitted this regression equation or estimated this regression equation, maybe I will get pi I less than 0, or maybe I get pi I greater than 1. So I shouldn't use this one at the left-hand side. What about using the odds ratio for the left-hand side? Like using pi divided by 1 minus pi equal beta 0 plus beta 1 xi. Using pi I divided by 1 minus pi I equal beta 0 plus beta 1 xi. It will be much better because the range of pi I divided by 1 minus pi I is between 0 and infinity. But maybe it will give me some negative. So let's use something much better than using pi I or odds ratio. Use log of pi or of pi divided by 1 minus pi. Because the range of this one is from negative infinity to infinity. So it's better to fill the model that log of pi divided by 1 minus pi or pi I equal beta 0 plus beta 1 xi. This one is much better. Why? Because the left-hand side never be greater than, the left-hand side, it will be between negative infinity to infinity, and the right-hand side can give me any value within this range. So I shouldn't use the simple linear regression. I shouldn't use the odds ratio only to fit as a response variable. You should use the log of the odds ratio as a response variable. So in this case, if you used this one, if you fitted this equation, or if you estimated this equation, or if you estimated beta 0, beta 1 for this equation, it will be much better than the simple linear regression. And you can write this equation as a log of pi divided by 1 minus pi equal beta 0 plus beta 1 xi, or you can write it down as a function of odds ratio. So pi divided by 1 minus pi equal e to the power beta 0 plus beta 1 xi. Or you can write it down as pi I equal e to the power times divided by 1 plus e to the power. So you can write the equation in terms of this one or this one or this one. All of them are the same. And the probability in this case never be less than 0 or greater than 1. This is called logistic regression. So how do I fit the logistic regression? The estimation. There is no closed form for beta 0, beta 1 actually. You know, in the simple linear regression, we are using the least square regression method. we will find a closed form for beta 0 and closed form for beta 1. But if you use logistic regression, there is no closed form for beta 0, beta 1. So we use the maximum likelihood estimation. So you maximize, you try to find some values. The function in R will try many different values for beta 0 and beta 1 and find the two values that maximize the likelihood function. What about testing? Maybe after estimating beta 0, beta 1, I would like to test beta 0 is significant or not, beta 1 is significant or not. We do not depend on residuals, as in the multiple linear regression and simple linear regression. We work with something called deviance rather than using the residuals. What is the deviance? Deviance is -2 times the log of the likelihood of the model with no explanatory variables. It has only the intercept minus log of the likelihood function of the model that has all the explanatory variables. Which one? Which in this case, one explanatory variable, because we work with a simple case so far. So we use these deviance for testing beta 0, beta 1, significant or not. So I use the GLM function, not LM function, generalized linear model. I gave the response, I gave the explanatory variable, I gave the data distribution binomial, and gave the data, which is saved under GLM. And it gave me beta 0 estimation using the maximum likelihood estimation, beta 0 value, and beta 1 value using the maximum likelihood estimation. And see, the beta 0 is significant, beta 1 is significant. When you look at the beta 0, beta 1 for the linear model, beta 0 were not significant, but in this case. So what is the equation in this case? Now I have beta 0 -3.75 and beta 1 1.34. Now we can write down the equation as log of pi I divided by 1 minus pi I equal beta 0 -3.7534 plus 1.3422 times xi, or the number of hours a student study for the exam. Or you can write it down as pi I divided by 1 minus pi I equal e to the power -3.7534 plus 1.3422 xi. Or maybe you would like to write it down as a function of pi I. So pi I equal e to the power -3.7534 plus 1.3422 xi divided by 1 plus e to the power -3.7534 plus 1.3422 xi. So now I plug in xi, it gave me the effective values for pi I, or give me the predicted value for pi r, or the predicted probability of success at some given value for number of hours a student study. What is the AIC, this value? This AIC value looks like something like in R squared. Do you remember R squared? R squared is used to see how much the explanatory variables can explain the variability in the response. And we use R squared to select which model fed the data well. So if I have two models, the one has the higher value for R squared is better than the one has smaller value for R squared. So in logistic regression, we use something called AIC, or Akaike information criteria. The smaller, the better. So if I have two models, if I fed the two models for the data set, the same data set, and I would like to know which model is better, I use the one has a smaller AIC. This is very common in logistic regression. So can I find a 95% confidence interval for the model parameter? You can do it for the beta 0 lower limit and upper limit, or beta 1 lower limit and upper limit. This one for beta 0, this one for beta 1. Can I get the odds ratio for the intercept and the explanatory variable? This is the odds ratio for the beta 0, and this one the odds ratio for the number of hours. Can I get the 95% confidence interval for the odds ratio? This is the first odds ratio for the intercept, odds ratio for the number of hours. This is the lower limit, upper limit, lower limit, upper limit. And the code that uploaded on R can give you this output. Can I test the whole model is significant or not? You can do it. You can find the p-value based on the chi-square test, and this p-value is very small, so the whole model is significant. So now, as I did in 2 minutes ago, this is the model in terms of the log or the logit of pi I divided by minus pi I. This is in terms of the odds ratio. This is in terms of the probability. All of them are the same. If I'd like to graph the function, the probability function, this is a graph of the probability function. This one is much, much better compared to the one we use, the one for the simple linear regression. This one is the one for the simple linear regression, which is expected value of yi, which is pi I, equal beta 0 plus beta 1 xi. It's very clear this one fits the data better than this one. And this one never be greater than 1, never less than 0. So you can use this equation to predict the probability of success at some given value of the number of hours a student study for the exam. So, for example, if I ask it to predict the probability of passing the course or passing the exam for a student to study 7 hours, so x equals 7. So if I would like to get the probability, pi I, so now pi I equal e to the power negative 3.75 plus 1.34 using only 2 decimals times 7 divided by 1 plus e to the power negative 3.75 plus 1.34 times 7. The probability is 0.996467. If someone studied 7 hours, the probability of passing the exam is 0.996467. What about the odds ratio? I can find the odds ratio in different ways. Like you can, because you have pi I. So pi I divided by 1 minus pi I, it gives me the odds ratio. So odds ratio equal pi I hat divided by 1 minus pi I hat. It is 0.996467 divided by 1 plus 0.996467. And it is the same thing. This one equal e to the power negative 3.75 plus 1.34 times 7. It is the same thing. This one, it gave me 282.02. What does it mean? It means if someone studied 7 hours, the probability of success is 282 times the probability of failing the exam. So almost sure you will pass the course. So now let's cover Bayesian. In Bayesian, you define the data distribution, and using the data distribution, you get the likelihood, and then you define prior distribution for the parameters, and then multiplying the prior distribution by the likelihood, you get the joint posterior distribution, and then you can find the conditional posterior distributions, use the conditional posterior distribution to generate a random sample from each posterior distribution using the Gibbs sampler. So what about the likelihood and the prior? In this case, we have only 2 parameters, beta 0 and beta 1. Let's assume the data distribution is Bernoulli, and actually it's Bernoulli because each person will fail the course or pass the course, fail or pass, fail or pass, and so on. So it follows Bernoulli distribution with some probability of success pi I, and beta 0. Let's have a prior distribution is normal. Beta 1 has a prior distribution normal. Prior distribution normal with mean A0, beta 0 for beta 0, A1, B1 for beta 1. What about the values for A0, B0, and A1, B1? I can use any values based on the information available. Maybe there are some information available, maybe there is no information available. So any function of pi can be used actually. It's not logit pi I. You can use anything else. You can use pi I divided by 1 minus pi I, or the odds ratio equal beta 0 plus beta 1 xi. And the values for beta 0, beta 1, and A1, B1 can be used to express the belief on the model parameters. If there are some available information, you can use it to find beta 0, A0, A1, B0, B1. Or if there is no information, use A0 equals 0 because you don't know beta 0 is negative or positive. Use A1 as 0 because you don't know beta 1 is negative or positive. But use a big value for B0 and big value for B1 if you have no information. Because bigger value for the variability, it means a big uncertainty means a less precision. In the open box, they use a very small value. Why? Because they use the precision. They do not use sigma square. So if you use precision, you use very small value for beta 0, very small value for beta 1 that represent very big value for variable for the variability. So let's go to the R code and run the analysis using Bayesian approach. Find beta 0, beta 1 using Bayesian approach. Write down the equation. And before you write down the equation, make sure the convergence happen using the Gellman-Roppen and the effective sample size and the trace plot and the standard error method. And then once you get beta 0, beta 1, plug in them in the equation. And now you have the predicted value equal. And after you get this one, predict the probability again of passing the course for a student studied 7 hours. So X equals 7. And also find the odds ratio and compare this probability and this odds ratio to the probability and the odds ratio we calculated for the frequency approach. So you compare the probability to this one, the odds ratio to this one using Bayesian approach. So now let's go to the R lab generalized linear model with one explanatory variable and then extend to the multilinear regression or the logistic regression with many explanatory variables. It will be very simple to extend. So let's cover these two R codes. Thank you so much, guys. And see you in a few minutes in the next videos. Thank you.